What's up? In this video I'm covering GANs N Roses stable, controllable, diverse image-to-image translation works for videos too. I love the title. I mean, I think it's totally appropriate given that they are generating anime images, so yeah, just roll with it. By Min Jin Chung and David Forsyth from the University of Illinois. And let me just dive straight into what the paper is all about, and it's about creating these cute images, basically anime images. So basically they feed in the content image here, and they pick different styles for every single column using this thing called style code vector, and we'll soon see what it is. And as you can see, so they just pick a style code and they keep it the same across the whole column. And one thing you can notice here is, so first things first is that you can see that this hoodie here is preserved because the content code is the same across this whole row, whereas the style code is changing. And same thing here, you can see this this formal color, and it's being kept across the whole row because, as I said, the content code is fixed, whereas the style code is changing. On the other hand, if we just focus on a single column, there we have that the content code is changing because we are having different input images here, right? But like the style code is kept the same. And you can see that it's kind of interesting because you can see that the style is kind of kept, although it's obviously very vague concept. And yeah, let me just show you one more thing, and then I'll show you how this thing works. So this is what they get as a emerging phenomena, basically from their whole pipeline, is that even though they don't train the system they don't have any temporal kind of a loss or constraint. Despite that, they can gain really consistent frames. So you can see here different input images, so they'll yield different content codes, but the style code is kept the same. And so you can see that basically it looks really consistent, like just going throughout the frames. You can see that the head pose here is the same as here, but the style code, so basically the style is the same. So you can see this pointy beard being the same there and here, and that's really cool. Without any temporal constraints, they achieve this. If we compare their result with this baseline council GAN, you can see that first things first, so this looks terrible, like this eye is kind of frightening me. And the second thing is that you can see that the style is changing, and basically you can see here the chin is kind of rounded. Here we have a pointy chin, so it's not consistent across the frames. So that basically means that the style is changing as well. And it should have been kept fixed, but this method is failing to do that. On the other hand, what they do here is they take this first frame and they take this last frame, and this time, so again, the content code is kind of determined by the input video, and they are just kind of randomly sampling different style codes. And so you can see that this image here has a totally different appearance compared to this one. So they are totally two different animes. So the style varies a lot. Here, even though they sample random styles, they still get decently similar images. So if you take a look at these two, you can see that these two have almost the same face. The only thing that's different is kind of the hair color and the background color, but they're mostly the same. The eyes are the same. So it's failing to create diverse set of anime avatars. So those are the main points of this paper. So they show that they can have really diverse set of avatars. They show that they can have this consistency, and that's pretty much it. Let me now show you how it works. I think the results are pretty impressive. So let's start from the beginning of the paper. So we show how to learn a map that takes a content code derived from a face image and a randomly chosen style code to an anime image. We derive an adversarial loss from our simple and effective definitions of style and content. This adversarial loss guarantees the map is diverse. A very wide range of anime can be produced from a single content code. So they're stressing the diversity, and basically, yeah. So the most important step is to be exact about what is intended by content and what is intended by style. So we adopt a specific definition. Content is what changes when face images are subject to a family of data augmentation transformations, and style is what does not change. It's as easy as that. And as you can see, it's coupled to the definition of that set of augmentations, and they say it somewhere here. So basically, so note that this definition is conditioned on the augmentations. So different sets of data augmentations will result in different definitions of style. So having said that, let me just walk you through the pipeline. So let me explain how this works. So first things they do is they form a batch of input images, okay? And how they do that is they take a single image, so maybe this one, and they apply a bunch of different geometrical type of augmentations, like scaling, rotation, etc. And so that's an important thing I want you to understand here. So they don't take multiple different images. They take a single image, they apply a bunch of different augmentations, and then they feed that into this encoder. So now what the trick here is as you can see, we have encoder, we have decoder, which kind of generates the anime images. Then we have additionally the second branch that again encodes this and decodes this. And as you can probably assume already, this is this will lead to cyclic consistency loss. But let me first focus on so there are three components to the loss function. The first things first is that this style code, so these are the style codes coming from these images, and what I want to do is keep these the same. So because they have the same image and they're just applying augmentations, they want to make sure that the only thing that varies is the content code, whereas the style is the same, because that's their definition of what content is and what style is. So style is whatever remains the same, and so this thing will encode that whatever remains the same concept, and the content code will encode whatever changes concept, okay? So how they will enforce that these are the same is they'll just find basically variance of that, because again, imagine this S will be some, I don't know, like d-dimensional vector, and because they have a batch of B images, they'll have B times D matrix, and they'll just make sure that basically the variance across different vectors goes down to 0. So just formally written, that's variance of this batch of style codes should be one term that we are going to minimize. And obviously when variance is equal to 0, all of the vectors are the same. The second part is, so after they generate these images, they'll feed them back here. And as you can see, so they want to preserve the content code. So this C prime, they want to make sure that those are the same as these C's here. So what they'll do is they'll feed the same style codes here, and they'll take the content here, and they'll try to reconstruct the very same images as in the input batch. So they'll just do L2 distance between the batch of real images and the batch that had some augmentations applied, and between this batch of generated images. And by doing that, we kind of so the network will learn how to preserve the content code inside of the generated images. The third component of the loss will be basically adversarial loss. So that's that's this part, and this first branch is something you're familiar with, hopefully. So that's just your GAN, so adversarial loss objective. So we'll be training the discriminator to discriminate between a batch of real anime images and a batch of generated images, and on the other hand, we'll be training generator to learn how to trick the discriminator into thinking that whatever it generated comes from the real data set. So that's your standard GAN objective. But the interesting thing here is this mini batch. As you can see, mini batch standard deviation. Let me try and zoom in here. So this is just standard deviation. So what that does is the following. So if you just have this branch here, what will happen probably is that your generator can learn to basically collapse into a single image that looks realistic, and discriminator will be totally fine with that. It will just say that, okay, this looks real to me, but we want to be diverse. We want to have diverse set of avatars, and so what they do is they take these images, and from a certain layer here, I think they are using penultimate layer. We'll see the details a bit later. But they take the feature maps here, and they just form these like basically standard deviation statistics, and they'll use those to feed them into the second branch of discriminator. And what that does is the following. So that means that discriminator, i.e. the generator, will need to learn how to mimic the basically those standard deviations across the whole batch, and that will by kind of trying to mimic the same statistic from the real images, you will learn how to create diverse set of images. So that's the whole point of this thing. Now let's dig into a bit more details, and we'll see how all of those fit together. Okay, so just ignore these, I just verbally explained those. So this was the first component. So as you can see, the loss has 3 components. That's the adversarial component, so that's your classical GAN loss. You have the style consistency loss, and you have the cycle consistency loss. So the first thing is this, as I said. So they say here in a batch, as above, we expect all SIs, all the codes to be the same, and this is how we enforce that concept. And secondly, they have the cycle consistency loss, and they say here that we find it helpful to shuffle the style codes in a batch. So that's just a minor detail. Let me just show you the equations. So this part here is the encoder, so from Y to X. So that's this one. So they are just kind of mixing different notations here. They say here B to A, they say Y to X in the equation down there, but that's this, yeah, they want to say this thing. So that's that equation represents, you feed in the generated image here, and you out comes the content code and the style code. And so what I say here is, let me get back to the equation. So this is the generated anime image, and you feed back, you get the content and the style code, and then you feed it back so that very same content code, but you take the style code from the original images. So as you can see here, so those are so we take these style codes from the original augmented images, and we take whatever was generated here, and we feed that into this decoder. Okay, so that's what these equations say. And so a minor detail here is that, as you can see, so C comes from the ith image, but the style vector comes from the jth image. And what they did here by doing this is basically they are additionally encoding. So this cycle consistency loss can also have the style consistency loss mingled in. And I don't know whether, so this is obviously not that pretty conceptually, but I guess there was some heuristic and they figured out that helps them further enforce that style consistency component. Okay, and finally, just L2, that's how we do cycle consistency loss. So whatever we reconstructed, we want to make sure that it's in the image space, it's got a really small distance compared to the original augmented images. There is one more detail here. Additionally, they use this thing called LPIPS. So that's basically your perceptual loss from neural style transfer literature. So what happens is that, let me go back to the diagram here. So what happens is that they additionally, so they feed this image, so this is the input image, and this is the reconstructed image. They'll feed both of those through this generator and decoder, and basically they'll take certain feature maps from a certain layer, and they'll want to make sure that also in that feature space they're really close, looking at maybe again L2 metric. So that's that additional part that they have in the cycle consistency component. Okay. And finally, they have the diversity discriminator and adversarial loss component. So that's the part I mentioned with the GAN loss and with this standard deviation stuff. So let's see what they say. Our diversity discriminator exploits the mini-batch standard deviation trick used in the progressive growing of GANs paper to exploit this difference. In the penultimate layer of the discriminator, we compute the standard deviation of each feature and pass that into another FC layer, so that's fully connected layer. Our diversity discriminator outputs the real fake logits and the standard deviation logits. This means the discriminator can identify reliable differences in within batch variation. So that's basically what I already explained, and I'll just try to tell you one thing that confuses me a little bit here. That's the following. So imagine, so this is your decoder and discriminator, and basically what will happen once you feed this image? So let's say one image, maybe this one. Once you feed it to and you extract the feature maps from this penultimate layer, you'll basically have some activation volume. So those activations from this penultimate layer will look something like this. So there'll be, we'll have some, like, let me draw it like this. So this will be some height, this will be some width, and I'll just add a subscript here like L because we are looking at a layer L, and we'll have some number of channels. So basically this is a collection of feature maps for this particular image. Okay, so this will be C sub L, and that's just a single image. So that's maybe this first image. Now we do the same thing for the second image. So we'll again have a similar type of activation volume there, etc. And So the part that confuses me is that they haven't really explained how they are calculating these standard deviation statistics. So what I assume is they take a certain feature, like maybe this feature, so that's basically, let's call it Aij, and they're gonna compute the standard deviation across the channels and across the mini batch as well. So now I don't know whether they are actually aggregating those standard deviations across the channels, or whether they are just lumping that whole, so whether the final shape will be something like B times height L times width L, or are they going to aggregate across this dimension and just feed that? So it's kind of not clear. The technicalities are not kind of clear, and I guess you have to experiment and try a couple of things to see what works. I think what they did in the progressive growing of GANs paper is that they average across every single dimension, and then they just replicate it into a certain constant feature map, and then just append that to the activation volumes. But yeah, that part is not super clear. But the concept itself is hopefully understandable, and that's that they want to enforce that the generated images have the same similar or realistically looking statistics, which will make sure that we have diverse set of images. Okay, so having said that, let me continue here, and let's see the experiments and the results they got compared to the baselines. Comparing this GANs N Roses paper to these old baselines like Drit++, Console GAN, and Star GAN v2, what we can notice is that if we take two different style codes, here we get completely different images. So you can see that these two are, okay, maybe the pose is similar, but the eyes are totally different. The chin is, this is pointed chin, this is kind of round chin. And here the difference is even bigger, so the head is obviously bigger, the hair is different, the eyes are bigger, etc. So if we take a look at some other baselines, here you can see that it's pretty much the same picture, just the only thing that changes is kind of colors. Same thing here, and also like just take a look at this eye, like this is so creepy. And like there are some artifacts, but they look really similar. So there are some artifacts like this one, so they don't manage to create diverse types of avatars, whereas this GANs N Roses paper does. They also compare with this newer AnyGAN paper, and the same thing applies here. As you can see, applying 3 different style codes, they get like totally different like avatars. So you can see there's many differences between these 3, but taking a look at the AnyGAN output, you can see that these 3 only, like the only significant difference is maybe the eye, the color basically. And here you can also see the structure, the face, the eyes, and everything changes. So again, plus for the diversity component of the GANs N Roses paper. They did some ablations also, like here you can see that this is the thing I was mentioning. So basically, when you take this diversity discriminator branch and you just remove it, you can see that what happens is you get basically mode collapse here, and that means that all of these images are realistic, and so the GAN component will say everything is fine. But like as we can see, they are pretty much the same, and they're almost the same. Here, when we include the branch, we actually get really diverse outputs. And then from some other paper, they just tried this mode seeking loss, and they gained just a bunch of artifacts, so they just stuck with this diversity discriminator component. Okay, they also did quantitative comparisons between with the baselines, and just using these DFID and LPIPS metrics, which focus on the diversity of the images, and they also use the FID, so that's for phase inception distance, which just focuses whether the generated image is actually realistically looking and similar to the actual real avatars. And again, they just get basically much better performance compared to the baselines. So DFID should be as low as possible. You can see it's much lower than the baselines, just focusing on this selfie to enemy dataset. And FID is also smaller, and LPIPS is higher. So all of these 3 metrics basically rely on a pre-trained classifier like Inception, V3 model or something. And how they work is similar to the perceptual loss. So they just do some comparisons in the feature space, and yeah, so I won't be digging into how they exactly work, but main point here is that the quantitative results are comparable and consistent with the qualitative results we saw. They also have there is this other paper that created this technique called, so this Cepha paper, and they say that Cepha finds latent direction that corresponds to large semantic changes in a style-based GAN by finding eigenvectors of the style modulation weight parameters. We show that our style space is highly expressive and editable using these eigenvectors in figure 7. So basically, they somehow calculate these eigenvectors, and so every single image here was generated using a different style code, and once you add these eigenvectors, you can kind of make them have certain properties. So if you add this eigenvector 5, you basically get small eyes and sharp features. If you add eigenvector 8, you get abstract lines, and finally big eyes and dark hair if you add this eigenvector at 10. So just they show that this manipulation method kind of works for their style codes as well. Okay, that's pretty much it. I mean, this paper is pretty simple to understand, but the results are, I like the results a lot, and so I thought covering it. So yeah, hopefully you found this video useful. If you did, consider sharing and subscribing, and until next time, bye bye.